harbor waters off the coast of Italy, there are chunks of concrete that have been sitting underwater for over 2,000 years. Not crumbling, not dissolving, not weakening, getting stronger. Scientists who studied these ancient Roman piers in recent years discovered something that should not be chemically possible: a self-healing crystal structure forming inside the material as seawater flows through it, actually repairing tiny cracks and reinforcing the concrete decade after decade, century after century. Now walk into almost any modern city and look at a parking garage, a highway overpass, or an apartment building poured within the last 50 years. Cracks, crumbling edges, exposed rebar rusting through the surface. Engineers routinely plan for these structures to need major repairs or complete replacement within 50 to 100 years. The Romans built things that outlasted their entire empire and kept improving with age. We build things that start falling apart before the mortgage is paid off. And for roughly 150 years, modern scientists did not fully understand why. They had lost the recipe. This is the story of the single most used man-made material on the planet, a material so common that more concrete gets poured today over any 2-year period than the entire human race used across the whole of the 20th century. It is the substance holding up your apartment, your workplace, the bridge you drove over this morning, and the dam holding back a river you have probably never thought about. And almost nobody has ever told the full story of where it came from, who controlled it, and what it is quietly costing the planet right now. This is the history of concrete, the paste that built the world. Long before anyone poured a foundation for a skyscraper, ancient builders were already experimenting with something that behaved suspiciously like glue for stone. Around 6,000 years ago, in parts of the Middle East and North Africa, early builders discovered that burning limestone produced a powder which, when mixed with water, hardened into a solid mass. This was lime mortar, and while it worked reasonably well for holding bricks together, it had serious limitations. It was weak under pressure, it dissolved slowly in water, and it simply could not support the kind of massive, load-bearing structures that ambitious builders were beginning to imagine. For millennia, lime mortar remained a modest tool, useful but unremarkable, sitting quietly in the background of human construction. Then came Rome. Roman engineers driven by an empire that needed roads, aqueducts, harbors, and monuments capable of projecting power across 3 continents, stumbled upon something extraordinary, almost by accident. Near the town of Pozzuoli, close to the Bay of Naples, sat a particular kind of volcanic ash, the leftover material from ancient eruptions of the region's active volcanoes. Roman builders discovered that when they mixed this volcanic ash with lime and water, and then combined it further with seawater and volcanic rock, the resulting paste did something lime mortar alone had never done. It grew stronger over time, and it grew stronger specifically when exposed to the harsh, corrosive environment of ocean water, the exact environment that destroys almost every other building material known to human beings. The Romans called this material pozzolana, named after the very town where the volcanic ash was harvested, and they used it to build some of the most audacious structures in ancient history. The Pantheon in Rome, completed around the year 128 of the Common Era, still stands today with the largest unreinforced concrete dome on the planet, a record it has held for nearly 2,000 years. Roman harbors, piers, and breakwaters were poured directly into wooden forms sunk into the Mediterranean Sea, hardening underwater into structures that modern engineers still study with genuine astonishment. Roman aqueducts carried water across hundreds of miles using concrete channels that, in some cases, are still partially functional today. For centuries, historians simply assumed Roman concrete was durable because the Romans were skilled craftsmen who used high-quality ingredients. That explanation turned out to be badly incomplete. In a series of studies culminating in research published in the year 2023, a team of scientists, including researchers from the Massachusetts Institute of Technology, finally cracked the actual mechanism behind Roman concrete's legendary durability. Using advanced imaging technology, they discovered small, mineral-rich lumps embedded throughout ancient Roman concrete samples. Lumps that earlier generations of scientists had dismissed as evidence of sloppy mixing, a kind of ancient construction error. It turned out to be the exact opposite of an error. These lumps, called lime clasts, were reactive reservoirs. When water eventually seeped into tiny cracks forming within the concrete, decades or even centuries after the structure was built, the water would dissolve calcium from these lime clasts and recrystallize it directly within the crack, sealing the damage from the inside out. The concrete was not simply resisting damage, it was actively healing itself indefinitely, using a process the Romans almost certainly never understood on a scientific level, but had somehow engineered anyway through generations of trial, error, and careful observation of what worked and what did not. It took modern science roughly 2,000 years and some of the most advanced imaging equipment on Earth to finally explain what Roman hands had already figured out through pure persistence. But here is the strange twist in this story. Once the Roman Empire collapsed in the 5th century, this knowledge did not simply persist quietly in the background waiting to be rediscovered. It vanished almost entirely. The specific volcanic ash formula, the ratios, the techniques for mixing and pouring underwater, all of it faded from common practice across most of Europe. Medieval builders returned to simpler lime mortars and stone construction, and for over 1,000 years, nobody on the continent was building anything close to what Roman engineers had achieved with pozzolanic concrete. The recipe was not stolen or suppressed, it was simply forgotten, buried under centuries of political collapse, economic disruption, and the slow erosion of specialized technical knowledge that had once been passed down through Roman engineering guilds. It would take well over 1,000 years and an entirely different kind of ambition to bring concrete roaring back into the center of human civilization. And the man who did it was not a wealthy scholar or a state-sponsored engineer. He was a working bricklayer from Leeds, England, named Joseph Aspdin. In the early 1800s, Britain was in the middle of an industrial explosion. Factories, railways, canals, and rapidly growing cities all demanded enormous quantities of durable building material, and existing options, mostly natural lime-based cements and various regional mortars, were inconsistent, unpredictable, and often simply not strong enough for the massive infrastructure projects the industrial age demanded. Aspdin, working largely through personal experimentation, rather than formal scientific training, began testing different combinations of limestone and clay, burning them together at high temperatures, and then grinding the resulting material into a fine powder. In the year 1824, Aspdin patented his process, and he gave his invention a name that was frankly a masterstroke of early marketing. He called it Portland cement, deliberately choosing the name because the hardened material resembled the prestigious, expensive natural stone quarried on the Isle of Portland, a stone favored by wealthy builders across England. Aspdin's cement had no actual connection to Portland whatsoever. It was a naming choice designed purely to associate his humble factory-produced powder with luxury and quality in the public imagination. It worked spectacularly well. The name Portland cement stuck, and it remains the standard term for the primary ingredient in modern concrete to this very day, 200 years after a bricklayer invented it, partly as a branding exercise. Portland cement solved problems Roman pozzolanic concrete never had to face on an industrial scale. It did not require volcanic ash from one specific region of Italy. It could be manufactured consistently in large factories using limestone and clay that were available in enormous quantities across the world. It hardened reliably, it could be produced to predictable specifications, and it could be shipped, stored, and sold as a standardized industrial product. Within a few decades of Aspdin's patent, Portland cement had spread across Britain, then across Europe, then across the industrializing world. It became the backbone of the modern construction industry almost overnight, powering the growth of railway networks, harbor facilities, factory buildings, and eventually the skyscrapers that would come to define modern city skylines. But there was an irony buried inside this triumph that almost nobody noticed at the time. Portland cement, for all its industrial advantages, was chemically simpler and considerably less durable than the material the Romans had perfected 2,000 years earlier. It lacked the volcanic ash, the self-healing lime clasts, and the specific mineral chemistry that gave Roman concrete its extraordinary longevity underwater and in harsh conditions. Modern engineers reinforced Portland cement concrete with steel rebar to compensate for its relative weakness under tension, a solution that solved the immediate structural problem but introduced an entirely new long-term vulnerability, because steel rebar rusts, and rusting steel expands, and expanding steel cracks the surrounding concrete from the inside out. This is precisely why so many modern concrete structures built within the last century are already showing serious deterioration, while Roman concrete structures built without any steel reinforcement whatsoever continue standing, and in some cases growing stronger after 2,000 years. The industrial world had traded durability for scalability, and for over a century, almost nobody in the mainstream construction industry seemed particularly concerned about that trade-off. As Portland cement production scaled up across the 20th century, it consolidated into the hands of a small number of enormous multinational corporations. And this is where the story of concrete takes a considerably darker turn than most people realize. Today, a handful of massive companies control the overwhelming majority of global cement production. Lafarge-Holcim, formed through the merger of French cement giant Lafarge and Swiss company Holcim, Heidelberg Cement out of Germany, and Cemex, based in Mexico, together dominate cement supply chains across dozens of countries, giving these corporations enormous influence over pricing, production, and industrial policy on a genuinely global scale. This kind of concentrated corporate power over an essential industrial material inevitably creates opportunities for deeply troubling decisions made far from public view. And one particular case involving Lafarge became one of the most disturbing corporate scandals connected to the entire history of concrete. Lafarge operated a large cement factory in northern Syria, and when the Syrian civil war erupted and the region surrounding the factory fell under the control of various armed factions, including the terrorist organization known as the Islamic State, commonly referred to as ISIS, Lafarge faced a choice: shut down the factory and absorb the financial loss, or find a way to keep production running despite operating in an active war zone controlled by extremist militant groups. Lafarge chose to keep the factory running. According to United States federal prosecutors, the company's Syrian subsidiary made payments totaling approximately $13 million to armed groups, including ISIS, in exchange for permission to continue operating the plant and to allow the safe passage of materials, workers, and equipment through territory these groups controlled. This was not a minor administrative bribe. This was a multinational cement corporation making calculated payments to a designated terrorist organization specifically to preserve industrial output and protect corporate revenue, while ordinary Syrian civilians were living through one of the deadliest and most destabilizing conflicts of the 21st century. The case eventually made its way through the American legal system, and in the year 2022, Lafarge pleaded guilty in United States federal court to conspiring to provide material support to a foreign terrorist organization, marking one of the first times a major multinational corporation had been criminally convicted in the United States on charges directly connecting its business operations to terrorist financing. The company agreed to pay substantial financial penalties as part of the settlement. It was a stunning admission buried inside an industry most people never think twice about. A reminder that the concrete holding up buildings around the world sometimes carries a supply chain history far darker than anyone standing in that building could possibly imagine. And the corporate controversies surrounding the cement industry do not end with a single criminal case. They extend into something considerably larger and considerably harder to prosecute in a courtroom, because this next problem is not a scandal involving one company cutting a bad deal in a war zone. It is a structural, planetary-scale crisis embedded directly into the chemistry of how cement is made in the first place. Producing Portland cement requires heating limestone to extraordinarily high temperatures, a process called calcination, and this process releases carbon dioxide through two separate mechanisms simultaneously. First, the enormous amount of fuel burned to reach those high temperatures releases carbon dioxide, the same way burning any fossil fuel does. Second, and this is the part most people have never heard of, the chemical reaction itself, the actual transformation of limestone into the reactive powder that becomes cement, releases carbon dioxide as a direct byproduct of the chemistry, completely independent of whatever fuel source is used to heat the material. Even if the entire cement industry somehow switched tomorrow to 100% clean, renewable energy for all of its heating needs, a massive portion of its carbon emissions would remain completely unchanged, because those emissions come from the fundamental chemical process of making cement, not from the furnace burning the fuel. The scale of this problem is staggering. Cement and concrete production is responsible for approximately 8% of global carbon dioxide emissions, a figure that places the industry ahead of the entire global aviation industry and the entire global shipping industry combined. If the cement industry were treated as its own individual country, its total carbon emissions would rank it as the third largest emitter on the planet, trailing only behind China and the United States, and ahead of every other nation on Earth. A single industrial material poured into sidewalks, parking lots, foundations, and highway overpasses, with barely a second thought by anyone using them, carries a carbon footprint larger than entire industrialized nations, larger than every airplane and cargo ship on the planet combined. This creates an almost unbearable irony when you place it directly alongside the story of Roman concrete. The ancient Romans built structures using volcanic ash and lime that have survived, and in some cases actually strengthened for 2,000 years, all without steel reinforcement, without massive industrial carbon emissions, and without any of the chemical instability that plagues modern Portland cement. Modern engineers and materials scientists spent the 20th century racing to build faster, cheaper, and at a much larger scale than the Romans ever could. And in doing so, built an industry that pumps a staggering amount of carbon into the atmosphere every single year while producing structures that, in many cases, will need replacing within a human lifetime. There is a real, active scientific effort underway right now to close this gap, drawing directly on the 2023 discoveries about how Roman concrete actually achieved its self-healing properties. Researchers are experimenting with reintroducing volcanic ash and other pozzolanic materials into modern concrete mixtures, hoping to recover some of that ancient self-healing chemistry while still meeting the massive production demands of the modern construction industry. Other researchers are exploring entirely new formulations designed to capture carbon dioxide directly within the curing concrete itself, effectively turning a portion of the material's carbon footprint into a permanent, locked-in mineral structure, rather than a greenhouse gas released into the atmosphere. None of these solutions have yet been deployed at anywhere near the global industrial scale required to meaningfully offset 8% of the world's total carbon emissions. But the underlying science strongly suggests that the answer to concrete's modern sustainability crisis may lie less in inventing something entirely new, and more in properly understanding something ancient that modern engineers had simply forgotten how to use. Step back and look at the full arc of this story, and something genuinely strange comes into focus. Roman engineers working without any understanding of modern chemistry accidentally discovered a nearly perfect building material, one that grew stronger with age, healed its own cracks, and required no steel reinforcement to withstand the corrosive power of the open ocean. That knowledge was lost for well over 1,000 years following the collapse of the empire that produced it. A 19th century bricklayer reinvented cement from scratch, built an entire global industry around a chemically simpler and considerably less durable formula, and gave it a marketing-friendly name borrowed from an expensive natural stone it had nothing to do with. That industry consolidated into the hands of a small number of multinational corporations, one of which was later convicted in an American federal courtroom for funneling millions of dollars to a terrorist organization in order to keep a factory running inside an active war zone. And today, that same industry quietly generates more carbon dioxide than the entire global aviation and shipping sectors combined, making it one of the largest single contributors to climate change on the planet, hiding in plain sight inside sidewalks, driveways, and parking garages that almost nobody ever thinks to question. Concrete is not just the most used man-made material in human history. It is a material whose full story runs directly through ancient engineering genius, a bricklayer's clever branding decision, a corporate terrorism conviction, and one of the largest unresolved environmental crises of the modern era. And virtually nobody walking across a concrete sidewalk today has any idea that any of it happened. The paste that built the world carries a history far stranger, far darker, and far more consequential than the gray, unremarkable material itself would ever suggest. If this changed the way you look at the sidewalk under your feet, or the building you are sitting in right now, hit subscribe and let us know in the comments which part of this story surprised you the most, and share this with someone who has never once thought twice about the concrete holding up their own home.